Hey everyone! Welcome back to the channel. Today, we're diving into one of the most fascinating ideas in deep learning autoregressive image modeling. We'll start from the theory, understand the math, and then walk through a full PyTorch implementation together. So stick around till the end. It's going to be a pixel-by-pixel journey into the world of generative models. What is autoregressive image modeling? Autoregressive models are powerful generative models that generate data one element at a time, where each element depends on the previously generated ones. While autoregressive models are traditionally used in time series and language modeling, they've also become state-of-the-art for image generation. The key idea: each pixel in an image is predicted based on the pixels that came before it, like reading a sentence left to right, one word at a time. In this notebook, we'll use the MNIST dataset, a collection of handwritten digits. Each image is 28 times 28 grayscale pixels, and we treat it as a sequence of 784 pixels. To make training efficient, we sometimes break down images into smaller patches. The model will then learn the local structure of images, like how pixel intensities vary across edges or curves. The math behind autoregressive image models. Before jumping into code, let's understand the math. Given an image represented as a high-dimensional vector, x sad face x1, x2, x, where each x is a pixel, or even a pixel channel, an autoregressive model expresses the joint probability, x, as a product of conditional probabilities. In plain terms, each pixel is generated conditioned on all previous pixels in some predefined order, e.g., raster scan from top left to bottom right. For example, consider a 2x2 image. X equals x1 x2, px equals px1, px2 divides x1, px3 divides x1, x2, px4 divides x1, x2, x3, x4. Learning these conditionals is often much simpler than learning the joint distribution px altogether. However, disadvantages of autoregressive models include slow sampling, especially for large images, as we need height times width forward passes through the model. In practice, we train a neural network to learn these conditional distributions. And that's what we'll implement next. Autoregressive models model the joint distribution of pixel intensities as a product of conditional probabilities. This means, instead of generating the whole image at once, we generate one pixel at a time, conditioning on all previous ones. It's like telling a story one word at a time, where each word depends on the ones before it. Now let's walk through each cell in our notebook and understand what's going on. First, we import our standard libraries: OS for file management, Math for numeric operations, and NumPy for numerical computations. Then, we set up Matplotlib and Seaborn for visualization. These libraries help us visualize the images and data distributions later on. We also import PyTorch and Lightning, which we use for building and training our model. A quick note: PyTorch Lightning is a wrapper around PyTorch that makes training deep learning models easier and more structured. Then, we configure a few environment settings, setting a random seed for reproducibility, enforcing deterministic behavior on GPU, and selecting the appropriate device. If a GPU is available, we use it; otherwise, we fall back to CPU. Next, we set paths for dataset and pre-trained model checkpoints. We also define a function to download a pre-trained model checkpoint if it doesn't already exist. This allows us to skip training if we want to just run inference or sample images. The discretize function maps input images from 0, 1, floats to integers in 0, 255, as PixelCNN treats pixel values as discrete classification labels. We load the MNIST dataset using Torch Vision. The images are split into training, validation, and test sets. This split is important to ensure our model generalizes well and doesn't overfit. Data loaders are created for training, validation, and testing. These allow efficient batch loading of data using PyTorch utilities. We define a helper function show_ims to visualize a batch of images. This function uses torch vision's make_grid to tile multiple images into a grid and display them. Now we're introduced to the key idea, masked convolutions. In language models, autoregression is straightforward. We just predict the next token. But with images, we deal with 2D spatial structures. We don't want the model to peek at the pixel it's supposed to predict, or any future pixels. Hence, masked convolutions apply a mask to the convolutional kernel to zero out future pixels. A class called masked convolution is created to implement this logic. The weight matrix is multiplied element-wise by the mask before the convolution operation. Blind spots are a known problem with stacking masked convolutions. PixelCNN solves this using vertical and horizontal stacks. The vertical stack convolution looks only at pixels above the current one. The horizontal stack convolution looks at pixels to the left. This L-shaped context ensures full coverage of all previously seen pixels. To verify if our implementation is correct, we visualize the receptive field, i.e., which pixels affect the output of a particular pixel. This is done by back-propagating gradients from the center pixel. The higher the gradient magnitude, the more influence that pixel had. We do this visualization for horizontal, vertical, and stacked layers to ensure they behave as expected. Next, we stack these convolutions to see how the receptive field grows with depth. This is a key design. Each layer sees a larger context. With proper masking, we get full context without future leaks. Now comes the magic, gated convolutions. These improve PixelCNN by allowing more complex interactions. The idea comes from LSTMs. Instead of a single output, we split the output into two, apply tan and sigmoid, and multiply them. This gating mechanism allows the model to learn when to pass and when to block information. The gated PixelCNN module stacks vertical and horizontal masked convolutions, adds a residual connection for the horizontal stack, and applies the gating mechanism. Using all the blocks above, we now define the full PixelCNN class. It starts with masked input convolutions, applies a stack of gated PixelCNN layers, some with dilation for increased receptive field, ends with a 1-by-1 convolution mapping features to 256 pixel values. The forward function returns logits for each pixel, and calc_likelihood computes the negative log likelihood, which is then converted to bits per dimension. We also define a sampling function that fills in pixels from top left to bottom right, pixel by pixel, using the model's predictions. Training is handled by PyTorch Lightning. The train_model function checks if a pre-trained model exists. If not, it trains a new one using trainer fit. We also log validation and test scores. We can now sample digits using our trained model. We call model.sample and visualize the generated digits. As you'll see, the model generates realistic-looking MNIST digits pixel by pixel. A fun use case of autoregressive models is image autocompletion. We take an image, mask the lower half, and ask PixelCNN to fill it in. We run this on multiple samples and see the model generating different plausible completions, from variations of the same digit to entirely different ones. Next, we visualize the model's predictions using softmax. We compare this with the true distribution of pixel values in MNIST. We notice that softmax can result in unnatural predictions, like assigning very different probabilities to adjacent values. This is where discrete logistic mixtures can help a smoother way to predict pixel intensities. Finally, we show how a discrete logistic distribution looks, which is used in PixelCNN++. It models pixel probabilities with smoother transitions than softmax. And that's a complete walkthrough of the PixelCNN model implemented in PyTorch. We've covered masked convolutions, receptive fields, gated mechanisms, and image generation from scratch. If you enjoyed this deep dive and learned something new, hit the like button, subscribe for more AI content.